Okay, again, good morning to everyone in Australia. Appreciate you logging into this webinar on lithium-ion battery and some of the testing provided by F500 encapsulator agent. We're pleased to be able to present to you, and we again appreciate the invitation by the New South Wales Fire and Rescue. Let me share my screen. This is going to be a little different type presentation. It is not going to be a PowerPoint presentation because we were asked to really kind of review the chronology and the history that we have had with the F500 encapsulator agent over the years. And so this paper here does just that. It gives us this chronology that dates back 14 years when we first got involved with lithium-ion battery. And at the time we wrote this up, Germany was expecting to have 1 million hybrid vehicles on the road, and worldwide these number of vehicles was going to be increasing very much. And I know here in the US, we now have about 9 hybrid car manufacturers, starting with Tesla, Hyundai, Mercedes, Ford, Honda, General Motors, and I'm sure I missed quite a few. But our history with lithium-ion battery started in January of 2008. And we provided Bosch Industries, who is a manufacturer of lithium-ion battery packs for EV cars and hybrid cars. We provided them F500 encapsulator agent for them to conduct fire testing on lithium-ion batteries. In March of 2009, so we got over a year of testing, Bosch had conducted fire testing on batteries, both lithium-ion batteries and the nickel metal hydride batteries, utilizing plain water, foam, ABC dry powder, and F500 encapsulator agent. And the tests they conducted were not just on the lithium-ion batteries and the nickel hydrides, they were also on other production parts and their production equipment as well. So later, we were invited to come. So if you understand Hazard Control Technologies, we're located in Atlanta, Georgia in the US, but we have a subsidiary called Hazard Control Technologies Europe. We have offices in Frankfurt, Germany, and our HCT Europe folks were invited to Bosch headquarters in Stuttgart, Germany. And at that time, we were advised that they have chosen F500 encapsulator agent as their product of choice for extinguishing lithium-ion batteries. Now, what Bosch explained to us at that time is, unfortunately, gentlemen, we will not share all of our test results with you because we spent a lot of money running these tests, and we consider our information confidential, but they will share the test results with other agencies. In other words, they didn't want HCT to take these test results and go around to the marketplace. But they said, we will allow HCT to use Bosch as an official reference customer. And they have authorized us to use Bosch logos in our promotional activities with lithium-ion batteries. And so they have purchased F500 encapsulator agent. We have put in fixed systems. So the way Bosch had set up in their warehouse, since they had existing sprinkler systems in place. They have purchased 1,000-liter totes of F500. They have tied those in to the fire department connections so that when the fire department shows up and starts to put plain water through their sprinkler system, it will automatically proportion a 3% solution of F500 into their warehouses and production areas wherever they have the fire. Now, with that said, Bosch did communicate their findings to VDA and the automotive industry. Obviously, Bosch is making lithium-ion batteries for the automotive industry, and their testing, it was emphatically showed F500 encapsulator agent to be the agent of choice. So they shared theirs because they had an interest in the automotive industry and understanding how to protect EV cars. Because if it became a problem for the automotive industry, and you're negative in the marketplace, you're not going to see the advancements of EV cars. So they did share theirs findings with them. Bosch, again, will not share their internal reports with HCT Europe. However, they did share their findings with Baden-Württemberg Fire School. So what is that? Germany has 21 states. Baden-Württemberg is a state in Germany. It's one of the 21 states, and it's the state that has the headquarters of Bosch. And Stuttgart, Germany is located in the state of Baden-Württemberg. So when they shared their findings with the Baden-Württemberg fire school, Baden-Württemberg went into action because we have an issue. And it's the same issue you face in Australia is how are we going to protect ourselves and protect the firefighters and extinguish lithium-ion battery fires, both on the car side, but also things like Tesla walls. So they started using these findings from Bosch, and they started to do some other tests. So shortly after receiving these test results, Baden-Württemberg published application guidelines on the potential dangers on the website, and the application guidelines specifically reference the use of F500 encapsulator agent. Now, we will transmit these documents to the people who are on here. So if I look at this little thing here, I see that's document 2I. So let me come over here to document 2I. Our document has an overview by HCT. This is the translated article in English. And then if you want to practice your German, we provide the original German article. So this just discusses, the fact that they did the test, and F500s were recommended at 3%, 6, and for Class D, 3% would handle lithium-ion batteries, metal fires, burning magnesium dashboards, door frames, steering columns, diesel fuel, gas, ethanol. So this was an article that was written by, or I'm sorry, this is an SOG application note and guideline written by the Baden-Württemberg Fire School. And it goes in and it talks about the fact that these guidelines were developed based on Bosch's stuff, but also in cooperation with DACRA. DACRA is an accident research company. They're a testing lab. They're actually a little bit larger than UL. They do a lot of fire testing, and we're going to see some of their reports as we go down through here. Talks about the structures of the batteries, run times. Again, I'm going to transmit these reports. Here they talk about batteries and extinguishment with water. Lithium-ion batteries are sealed. The lithium metal, however, reacts violently with water, especially in damaged cells. that are electrically charged state. The reaction of lithium with the electrolyte as well as water produces hydrogen. This hydrogen can build up highly flammable and explosive mixtures, bearing in mind, hydrogen flames cannot be seen. So some of this came from the Bosch testing on lithium-ion battery with plain water. The issue there is they sometimes get a reaction depending on the the chemistry of the battery, and as we know, it takes copious amounts. Covering the fire with sand or metal cuts off the oxygen. However, this is hardly it cools. This method hardly cools, therefore not preventing the reaction between the lithium and organic components. So when removing the cover, we suddenly supply oxygen and we still have a smoldering fire. So they were looking at water, they were looking at using sand and covering. And then here, they said research carried out by a large corporation company, they're talking about Bosch, within the electrical industry had shown that there were two products, such as cold metal, which is a gel, and 3% F500 mixture, which is an encapsulating agent applied under high pressure, achieved very good extinguishment results. So Bosch was the one that kind of got us started here in the lithium-ion battery application. So this is one of the early on reports. As you see, that we're moving forward. The January 11th. So then we have an article that appears in Brand Schultz magazine discussing the use of F500 on lithium-ion batteries. So that's this article here, 2B. And this was published in March of 2011, discussing the technologies used in today's hybrid cars and the hazards associated with them. This article concludes with advice that for firefighting these high voltage vehicle cars was recommended F500. So here again is the original German article that can be used to practice your German. We have taken this article and translated it into English. And again, this is not a test report, but the article is based on various tests that are done early on, and it's talking about the different tests, fuel cells, and vehicles. Says water is proven to be a good extinguishing agent without additives. However, lithium-ion battery requires especially large amounts of water. Since the metal lithium-ion reacts violently with water, it may release hydrogen. Hydrogen-air mixtures are in large mix ratios, are ignitable and highly reactive. Tests were conducted by manufacturers of high voltage batteries using products such as cold metals and F500 applied to show good extinguishment results. When extinguishing, a minimum distance should be observed and so on. Firefighters may stay at least 1 meter away when using a dispersed spray pattern. So again, this is very early on based off of the Bosch testing. Then we had some additional testing and we get another article. This article 2C shows up in Brand Schultz magazine. It's talking about encapsulator agents for special risks. And here again, we have an overview, which I'm going to. So it mentions the F500 EU and F500.com in the articles. Here's the original. But I think to me, the interesting parts here are fires involving cars metals, plastic, rubbers, tires, lithium-ion batteries, photovoltaic systems, liquid glass, woods, alcohol, and now fighting a fire from an environmental protection point of view, quite possibly even in protected areas such as nature's reserve, an unsolvable problem. So what they're saying here is, wow, we have all of these different types of materials on a fire, on a car fire. And now if we want to fight these environmentally and fight these with in a practice that has good risk and good health to fire departments, firefighters, it could be unsolvable to say no, not for extinguishing agent, F500 encapsulator agent, and give us the website, and then they talk more about the additives, um, more about um, more about the Bosch testing, other users, in-house fire brigades who are using it. And then it talks a little bit about F500, what it is. How is this product different from a wetting agent? And how is this product different from foams? What is it doing? And how is it working on lithium-ion battery? I'm going to get back to that so that we understand better. So again, in this, we start to introduce DACRA. DACRA has run tests. They've confirmed the effectiveness of the firefighting on lithium-ion batteries, and therefore they're recommending F500 as an extinguishing system. So if I go back to this chronologically, here we see 2D. This is a press release by DACRA where they release and announce their test results and the final. So this is going back. This is again a Brand Schultz magazine, but this is DACRA's press release where they're showing all of their test results on F500. Now, I didn't highlight a lot of this because this is a little older and we have much newer stuff. But the gist in here is that DACRA tested it on lithium-ion battery. They also tested on other materials. During the DACRA test, they tested both F500 and a gel. I believe it was the cold um, case. But what they found was the gel worked, but only in a confined area. It didn't work in an open area. The F500 worked in both a confined space as well as an open space. And in addition, the F500 worked on all the other hazards that were on the car, where the gel was more confined to just if you can get it inside the battery compartment, it actually would put the fire out. Here they confirm their recommendation in an opinion letter. So this is a testimonial letter that came from DACRA talking about fire protection for lithium-ion battery. Actual combustion testing has proven to DACRA that F500 is more effective than other extinguishing agents in these situations. So this is their opinion letter. And this opinion letter got published here in the Brand Schultz magazine. So not only did they send this over to the automotive people, but also were referencing how the agent could be used in sprinkler water spray systems in accordance with the DIN code and some FM global requirements. So they highly are recommending the F500 for special applications. So moving forward, here in February of 2013, DACRA actually publishes a condensed version of their report. We have the DACRA report, we have the confirmation. We have the press release, their opinion, but they also published this in the magazine. And if we see here, we're 2F. So this talks about the report presented by Dacre Automotive, by Daimler, which is part of Daimler Chrysler here in the US, and Deutsch Automotive, and how these guys then came and presented in Detroit, Michigan at the SAE International Conference in 2013. So all of their testing that they did on lithium-ion battery was presented at this SAE conference. And that's really the next document. But as we go down through here, this is a short condensed version of the testing that was done by Dacre on lithium-ion batteries on energized cars. Again, they got a German version. Here they're showing they tested with the F500. This is what we refer to as an F500 encapsulator agent TKO nozzle. It's the delivery device. It's the F500 agent supply and an eductor all built in one device. The beautiful thing about this versus an eductor is once you disconnect the hose, there's nothing but plain water. There's zero waste. These nozzles come in two configurations. One is a 75 liter per minute nozzle that can do a half, 1, and 3%. And the other one is a 130 liter per minute nozzle that can do a half and 1%. We supply a lot of these nozzles here in the US, and we're typically supplying the 75 liter per minute nozzle, which is a 20 GPM, and we're starting to see them used on all car fires in the US, whether it's a hybrid fire or just a gasoline diesel fire. And I know if I have firefighters on here, this is blowing your mind. You're going, that's ridiculous. You're telling me you're using a 20 GPM nozzle, 75 liters per minute, and we're extinguishing fully involved fires in under 1 minute. It's beautiful. There's zero runoff. I know Australia is a very environmentally conscious country, just like F500 is, excuse me, just like we are at HCT and what the US is. So, you know, our fire departments are starting to look at how can I put the fire out without creating a lot of overrun. So this is again was published this is published by Dacre in Brand Schultz magazine. So they're talking about F500 again. F500 test 1, test 2. They tested a product called FireSorb. They tested plain water. I guess it might be better if I got to the English version here. Some of the things you see here is the temperature reductions, and you can see like a plain water takes time for the temperature to go down, and then you see it starts to come back up as soon as you stop the nozzle. One of the big difference here with the F500, temperature straight down and remains down. And we have some other tests that's showing that, and we can explain why this agent does that. So again, these are the Dacre tests published in Brand Schultz magazine. Um, 2H, this is the test report. This is Dacre, Daimler, and Deutsch Automotive. This is the test report. There's a quick overview. This is the English version, where they presented in Detroit, Michigan at the 2013 World Conference. Again, they're talking about the AWG nozzle. This is the F500 TKO. When almost any nozzle can do, the advantages of this is less water and no F500 waste in the hose. Stay away from the fire zorb. So these results got presented here, in a paper, um, explaining the tests. So they talk about a number of electric and hybrid vehicles equipped with high voltage batteries is rapidly growing in most countries. It's definitely growing here. Um, Having some issues. The lack of practical experience, especially with fire incidents, leads to interim guides, superficial information, and sometimes even instructions that are difficult to implement. And so that's what these guys were seeing. And this is the automotive industry. Dacra, Deutsche Automotive, Daimler. Um, they ran tests on lithium-ion battery, focused on learning more about the batteries. These were the test configurations where they put the batteries over top of heptane. The tray was filled with 45 liters of heptane, serving as an ignition source and burned for about 11 minutes. The fire extinguishing was started in 20 minutes. Um, all tests, the batteries were identical. Each battery was equipped with 6 thermocouples. So this is showing the batteries. Recording started at the beginning of the heptane and was stopped after the batteries were extinguished and the cooling process was down. Um, it talks here about the different nozzle types that were used. This was a 100 liter per minute nozzle. Here we used the 75 liter per minute, used a ratio of 1% here. We actually, in Europe, they've been doing testing at 1 and 2%. Here in the US, we recommend 3% because our listing for Class B is 3%, and our encapsulation ratio is 2.5%, which I can address in a minute. So here they talk about FireZorb had good fire performance on the small lithium-ion batteries conducted by Robert Bosch. Mixed with water, it forms a heat shield gel with a high cooling capacity to reduce water evaporation rate. So this is the FireZorb product. Test 1, it took about 8 minutes until the action of the lithium-ion battery became visible. Escaping gas led to flash fires with flames about 200 centimeters in length while the heptane was still burning. Short circuits led to bright white flames. A few grams of liquid aluminum were discharged through holes once the heptane had burned away. After 11 minutes, continued to burn in a self-contained fashion. The flames emerged from the pressure release devices were, clearly smaller in this phase without the heptane. Flames were up to 40 centimeters high. So it just talks about it directly above the fire. The temperature was 750 degrees C. So here they're showing 750 degrees C. The battery was extinguished with water, the fire extinguished. So here it took 40 seconds and 70 liters to extinguish the flames. Several short water pulses followed to cool heavy smoke, the white smoke. However, 144 seconds to 2 minutes later, after starting the extinguishment of the fire, the lithium-ion battery reignited. So now another 200 liters of water were used within the first 4 minutes. The lithium-ion heated up again, emitting large amounts of smoke. Another 200 liters were necessary to cool down to the level to stop the smoke. The extinguishment took 17 minutes, 30 seconds, and 400 liters of water were used. Here they're coming back just saying the values of the fluoride and chlorides seemed unusually high here. Again, used 400. Now on the second test here with the F500, the temperature registered by couple 3 rose to 1300 C. Well, the water, we go back here, rose to 750 C. So we're talking about a battery burning here that's almost twice as hot. The temperature registered 3 rose to about 13 for a few seconds. The channel temperature was 400 C, and so on and so forth. Here, the fire was extinguished using 1% F500. The flames disappeared immediately on initial contact with the F500. Took about 14 seconds and 15 liters to extinguish the fire. The temperature dropped in the same way as test 1. In contrast to test 1, they did not rise again. Altogether, less than 80 liters of water were needed in test 2. So they mean is less than 80 liters of really a 1% solution of F500. Says the tray was stored overnight in a tray filled with F500 water mixture. Then they come back and they took measurements of the fluorine and chloride. Nevertheless, the extinguished water can be discharged to wastewater lines connected to a wastewater treatment plant. And then I guess they're showing the electrical conductivity based for corrosion. But this is one of the big differences between using plain water and using an encapsulator agent is we have 3 separate test reports that are showing that the runoff with an encapsulator agent, you're not creating hydrogen fluoric acid like you are with water, and that the results of what you're getting with the runoff from an encapsulator agent extinguishment can be diluted down and run through a municipal or industrial wastewater treatment plant. On the other hand, the stuff with water needs to be treated. I know in Germany they use 5,000 liter containers of water, and they will dip the car into that water and just leave it in there. So you have a lithium-ion battery car on fire, they pick it up, they stick it into the container. Well, when they do that, they contaminate that water, and the current cost to dispose of that water is 700 euro per 1,000 liter tote. So if you have 5,000 liters, that's 5 times 700. Just the disposal cost of the water alone with that extinguishment method is 3,500 euro. And with the encapsulator agent, you can run it through the wastewater treatment plant. The fire sorb, I'll let you go through and read that. It took more, and it's a gel and doesn't handle all the other hazards that are on the fire. So when I transmit these, I'll let you guys go through these conclusions, because we're going to send all these documents over to you guys. Now, based off of this, DACRA presenting in Michigan, well, guess who was in Michigan? Ford, Honda, General Motors. So these guys were all there. And so then they started knocking on our door saying, hey, we need to understand more about F500 encapsulator agent. So we, HCT, went to General Motors, and we did some side-by-side tests with General Motors on lithium-ion batteries. The local fire department came. They had a 500-gallon tank, booster tank. They were using a 125-gallon per minute nozzle. They applied all 500 gallons and were not able to extinguish the fire. We used the 20-gallon per minute TKO nozzle. And the gentleman that conducted the test is actually on our meeting here. It's one of our firefighters, Mr. Jeff Monkowski. He used a 20-gallon per minute TKO nozzle, and he had a 2-liter bottle of F500. He was flowing at 3%, and then within 1 minute, everything was extinguished and cooled. He stopped the nozzle, unscrewed the bottle of agent because the 2 liters were gone, and he screwed another bottle in while we were talking with the General Motors people and the fire protection engineer, but never had to reuse any of the 2nd liter. The fire was out, the temperature was down, and it never rose again. As a result of that, we have been used at the General Motors specifies the encapsulator agent for use in their lithium-ion battery abuse lab. So we come here, and this is a General Motors specification. Here's lithium-ion battery abuse lab. We're dating back now to 2015. Here they're specifying encapsulator agent. So the fire suppression agent is F500, manufactured by Hazard Control Technologies. The installer of the system was Shambaugh and Sons. The agent was UL listed. It's listed and approved, for mix with plain water, rivers, or seawater. 100% biodegradable. The agent is free of PFOS and PFOA. The agent had to have a corrosion rate less than 200 per year. So this is just the specification on the agent. And then this was the specification on our F500 agent bladder tank that was used. So on this project here, we have 2 battery abuse tables. You can see one of them here on the left, and the other one's over here on the right. And I suppose if I blow this up a little bit, we can see that we're providing an F500 fire protection system under the flume. So we did a design here using a sprinkler density of 0.2 gallons per minute per square foot, a proportioning rate of 3%. And this was installed by Shambaugh and Son. Now we know when they have a discharge, because one of the services we provide is coming back out and refilling the tank. And they've had a discharge, and we've gone back and refilled the tank. And obviously it was a successful fire extinguishment because the building's still standing and the fire was out. So Tesla specifies F500. So the history here is now Tesla's was at that show. They've seen the results that are coming on F500. So we actually meet with Tesla out at the Gigafactory, and we also meet with Panasonic. And one of the things they're interested in is, what is an encapsulator agent? How is this different? How does this work? And so let me take you through a few slides, just describing that, just so we're clear on what's different. Okay, so a quick review. This is a simplified version of the molecule. Polar head loves water, dissolves in water. I always remember polar bears love water. The non-polar tail hates water. It will do absolutely anything it can to get away from water. So when the molecules go into solution, and this could be through an eductor, a water-driven proportioner, a ratio controller, could be premixed, they automatically conglomerate and orient in this configuration. The polar heads are outward because they like water. The non-polar heads are inward because they hate water. The non-polar tails hate water. And so we form a basic building block of an encapsulator agent, which is technically called a spherical micelle. And what we're looking at here is something that's the size range is about 1 times 10 to the minus 10th. It's measured in angstroms. So we have millions, literally millions and billions of these coming through the hose. And they exit the hose. What happens is the micelles closest to the surface break apart, and now we form a skin on the surface of every droplet. And inside, we still have hundreds of thousands, if not millions, of spherical micelles. So this is different than a wetting agent. A wetting agent doesn't have these spherical micelles. Obviously, a foam doesn't have them. We all know the basic building block of foam is a bubble, and we put hundreds and thousands of bubbles together to form a blanket, and we're mechanically separating the fuel from the oxygen to smother the fire. Our basic building block, this spherical micelle, encapsulates the fuel inside the spherical micelle. So we're separating the fuel from the oxygen. We're just doing it on a chemical molecular level. So when we take a look here, between plain water, we have H2O on the surface and H2O throughout the whole droplet. Here, we've changed the substance that's on the surface. Now we have an F500 molecule on the surface. We have H2O molecules in the interior, and we have millions of spherical micelles inside. So the micelles do 3 things. The first thing it does is it encapsulates. These micelles encapsulate fuel molecules, gasoline, heptane, Jet A, alcohol, the electrolyte. It also encapsulates other things like hydrogen, the HF gas that's coming off, CO, SO4, SO2. These are things that we know we encapsulate, and we encapsulate whether the molecule we're encapsulating is in a liquid phase or a vapor phase. So as a result of this technology, there's a brand new standard that has come out in January of 2022. And one of the sections in that new standard is actually flammable liquid vapor encapsulation explosion prevention systems. And all of that is based on this spherical micelle technology. And we'll get to 18A here in just a minute. So basically what we're doing is we're encapsulating the fuel molecule inside the spherical micelle. Now, the reason we have 15 fixed system projects at the Tesla Gigafactory is because we went to Tesla, met with Tesla and Panasonic, and they said, look, this electrolyte is flammable. Show us what this micelle can do. So they gave us the electrolyte. We put that in a pan. We put our agent in the pan. We mixed in water, and we encapsulated Panasonic's electrolyte. So in one pan, we had electrolyte and water with no agent. In the other pan, electrolyte, agent, and water. Then we took a propane torch and easily lit off the flammable electrolyte in the electrolyte and water only pan. But Panasonic stood there for 5 minutes putting that blowtorch over the encapsulator solution, and they could not get their electrolyte. to catch on fire. So that's one of the differences between F500 and the water, is the encapsulator agent encapsulates any exposed electrolyte within the chemical cocoon, within the spherical micelle, thus rendering it non-flammable and non-ignitable, even if the temperature comes back, because we were putting temperature on that encapsulated electrolyte up to 1500 degrees F. So that's one of the critical things here. This is just showing, again, a spherical micelle with the molecules encapsulated inside, separating the fuel from the oxygen on a chemical molecular level. The second thing that I think is very important to understand is here you have plain water, and it has a molecular weight, it has a boiling point, and we know very clearly the heat reduction mechanism of plain water is steam conversion. So the outer molecules of this water droplet heat up from the room temperature where they come out of the sprinkler head up to 212 and convert to heat, and that's what slowly reduces the heat. We changed that. The molecular weight of our agent is 50 times bigger. You can see the boiling point is different, but I ask you, don't fall in love with this stuff. Fall in love with this. We change the heat reduction mechanism of that droplet from steam conversion to thermal conveyance. And that's kind of a new terminology. And I've had fire protection engineers say to me, you can't change physics. And I said, we're not changing physics. We're changing the substance. And let me show you what I mean. This right here is a wooden stick. And if I take a blowtorch to this wooden dowel, I can heat this up. I can catch this on fire. I can dance around the room, but the heat doesn't transfer very effectively down to my hand. It just stays here. This is analogous to your water H2O molecule. Oh, but what are we doing? We're changing the substance that's on the surface to an F500 molecule. And this is a piece of metal. This is an aluminum. This conveys heat. So now when I put the blowtorch here, it goes down to my hand. Oh, I can't hang on to it because the heat is transferred very, very quickly. And so that's what we're doing here, is we're changing the heat reduction mechanism of this droplet. I like to say, think about the heat transfer capabilities of a plain water molecule is like riding a bike. It's very slow. The heat transfer capabilities of this new substance, the F500, is like a Ferrari. So as this droplet is coming onto the lithium-ion battery, what we're seeing is we're transferring heat like a Ferrari through the F500 molecules on the surface. These micelles, and there's millions of them inside, are bouncing around. They're coming in contact with the molecules on the surface. The heat is very fast, like a Ferrari, being transferred around the surface of these micelles, and then ultimately, like a bicycle, into the water, drop into the water molecules inside the droplet. So we're creating a heat sink. So here's your plain water coming out of the hose. It's coming out at 70 degrees F. The droplet, let's say 95 to 97% of it remains right at 72 degrees. The outer part, like an onion, converts to steam. You get marginal heat reduction, and you need to use copious amounts of water. With the F500, we're coming out at 70, but we're transferring the heat to the internal portion of the droplet, 80 degrees, 90, 100, 110. And since you steam at 212 Fahrenheit, and we're only at 1 to 110 Fahrenheit, we do not create any steam. We're absorbing the heat into the internal portion of the droplet. And when we talk about thermal runaway and lithium-ion battery, geez, everything that I've seen and read from NFPA says, and UL and FM Global, the big problem is thermal runaway, reduction of the heat. We need copious amounts of water to reduce the heat. Here's why. The water is not very effective to reduce the heat compared to the F500. The F500 reduces the heat 10 to 20 times faster than plain water. Let me make sure I'm saying this correct. The same volume of a 3% solution of F500 will reduce the heat 10 to 20 times faster than the same volume of plain water. And it will do it without creating superheated steam. I know we're talking lithium-ion battery, but one of the big things and movements we're seeing here is F500 being used for interior structural attacks. Here's showing a comparison. This was a university study, heated up some steel coupons, applied F500 on one of the steel coupons, and the thermocouple measured within the first couple of seconds a reduction from 1150 down to 100. So very quick heat absorption. And on the second thermocouple, steel, put a foam blanket on, we can see we had a reduction from about 11 to 950, but then the blanket kind of kept the heat in. So, you're seeing different mechanisms here of heat reduction, and that's one of the big keys to the encapsulator agent. The third thing that this agent does, the micelle interrupts the free radicals. So when free radicals come together, or what's typically known as coalescence, when they come together, here's two free radicals in my hands. When they come together, that's what forms the toxic soot and smoke. And so we've had tests that demonstrate over here you're burning toluene, and when you put plain water through, the smoke is coming up. We have a light shooting through here onto a device that's receiving the light. The air is being sampled, and in this test, Clemson University, this is their Department of Environmental and Wildlife and Environmental section, was measuring the soot accumulation. Then over here, reran the same test, this time with the 3% spray of F500 across the smoke flume, and we see a 68% increase in visibility because we had a huge drop in the amount of smoke. So way more light was going through. The soot accumulation was 97% less, and the soot toxicity, what got sampled from the air sample, was 98.6 less reduction in toxicity. So I know we're talking about lithium-ion batteries here, but here in the US, we're seeing a big movement of utilizing this agent because of what it does to improve the IDLH environment and take away the toxicities that are causing cancers to firefighters. And I know firefighters say, well, we're coming into the environment, we have SCBAs on. There was a recent study here by the University of Illinois, Dr. Fent, where they took exhaled breath of firefighters before and after, and found that just through absorption in the skin, they took on 25 more parts per billion of benzene than they had prior to going in. And that was all through absorption. So when we look at this agent, we're encapsulating benzene that's off-gassing from plastics. We're knocking down the toxic soot and smoke to increase visibility. We're rapidly reducing the heat without the creation of superheated steam, without the creation of any steam, and we're rapid knockdown, keeping you in that environment less. So we're seeing major movements here from PFOS, PFOA foams into encapsulator agent. So this is just some of the toxins that we have clearly identified through 3 different test reports that we take out. Now, I'm going to end this slideshow. I just want to show a little bit about what the encapsulator agent is doing. So on the lithium-ion battery, what's separating the F500EA from other items like foam and dry powder is, one, we're encapsulating the electrolyte, rendering it non-flammable and non-ignitable. And secondly, what we're doing is we're rapidly reducing the heat, and the heat is staying reduced to protect against burn back resistance and thermal runaway. This was a test here done with Kiwa. I need to talk a little bit about this test. This was done in the Netherlands. Kiwa is a third-party testing site. They're acceptable to the authority having jurisdiction in Europe. The test was actually jointly conducted by Johnson Controls Europe and Hazard Control Technologies Europe. I want to make sure we're clear, give you a little background. Tesla and the Netherlands said we need to have fire extinguishers that can put out lithium-ion batteries. So the local fire extinguisher distributor, they are a fire extinguisher distributor of Neuropene. Neuropene is a fire extinguisher company located in Germany, and they are a division of Johnson Controls. So based on all of the testing that's been done and the success and the actual application and use of F500 encapsulator agent in Germany, we have developed a good relationship with Johnson Control. Even though we're competitors, we're friendly competitors, and Johnson Control asked, Neuropene asked Johnson Control Europe if they could test F500EA in their fire extinguishers. Well, Johnson Control said, we don't know. So they asked Johnson Control in the USA. And Johnson Control in the USA gave them the authorization to do this test. However, Johnson Control USA said you need to test every fire extinguisher configuration that is manufactured by our company, Ansell and ChemGuard. So Johnson Control owns Tyco. Tyco owns Ansell and ChemGuard, which are 2 of the largest foam manufacturers in the world. And they also own Williams Fire and Hazard Control. Over in Australia, Johnson Control owns Tyco, Warmold, probably a bunch of others. So Johnson Control's really the largest entity, fire protection entity in the world as far as supply. So this is just a test result that says, hey, we want to go ahead and see that can these handheld portables meet EN 3.7. So they had an overview of the test. So here they used foam fire extinguishers, they used dry powder fire extinguishers, and they used F500 fire extinguishers. So they used 9-liter units. So there's the agent. This was the battery pack that was used. They used glow plugs to start the batteries. In these tests, they didn't really monitor them with a bunch of thermocouples. Used these to overcharge the batteries. They used dry powder, foam, and F500. And here were the results. The dry powder was pour, pour, and pour. It didn't put the battery out. Do not apply on a lithium-ion battery. The foam was moderate, pour, moderate, not recommended for application on lithium-ion battery. And then the F500, sufficient, 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 and can be recommended for lithium-ion battery. So this was the conclusion of the testing. We have a video, a quick video of the testing. stop this right here because we have a battery here that has some A components. It has some B, the electrolyte's flammable, has some C components, and not all of them have D, but some of them have D components. Um, I guess by default, because these batteries are not in their own classification, they tend to fall under Class A. Just keep that in mind because after this, I want to talk a little bit more about that. So here we have a dry powder on the left. This is a typical ABC dry powder fire extinguisher, probably the #1 sold fire extinguisher around the world. In the middle is a Class B AFFF foam extinguisher, and on the right is the F500. These are the videos from that Kiwa test. You see they're starting to apply the foam in the middle. Started back, now he's coming a little closer, trying to get a blanket on top of that. Pressure itself is just blowing the bubbles off. So when I see this video and I start to think about this hazard, again, it's a multiple type hazard, and by default, we seem to want to treat this like it's a Class A fire. And we know that ABC dry powder fire extinguishers is the #1 extinguisher sold in the world. And if this is an A fire and an ABC can't put it out, that makes me think perhaps we're not really dealing with an A fire. And then if you think about what is the #1 fire Class A fire extinguishing agent in the world, it's plain water. And geez, every test report I look at says we must use copious amounts of water. Well, the reason we're using copious amounts of water is perhaps lithium-ion battery is not a Class A fire. So on Monday and Tuesday of this week, I was in Boston at the NFPA annual conference and was having discussions with the people within NFPA, and we have now been advised how to submit a proposal to NFPA and the Standards Council to classify lithium-ion batteries as a Class L fire. And when I look at this and I think about every commercial building has an ABC dry powder fire extinguisher, and every commercial building has a lithium-ion battery cell phone, iPad, computers, UPS power stations, and you're going, this isn't going to work. But the only way to correct this problem is to put lithium-ion battery as a Class L, get testing protocols for Class L, and then update the codes accordingly. So that was part of the testing for that's the Kiwa testing. So there's a test report that shows what they did, how they did it, and there's a video there as well. Okay, my stuff kind of stops here at 2017. I'm going to transmit this to the folks on the call here. I do want to show this. This is Neuropene lithium-ion batteries. They talk about F500 portable fire extinguishers, reliable protection. So what happened was we did those tests that you witnessed on a Monday. Now, I wasn't personally there, but the president of Hazard Control Technologies Europe was there. Um, Johnson Controls ran tests on Tuesday, Wednesday, and Thursday. HCT Europe was not invited to any of those tests. There they tested the dry powders, um, nitrogen, CO2, foam, everything that Johnson Controls has in their arsenal. On Friday, Johnson Controls contacted HCT and said, we don't have a good solution. You have the solution. We want to partner with Hazard Control Technologies and make portable F500 fire extinguishers for lithium-ion batteries. So hence, we said, but why would you do that? Why would you, come out and say, we have the solution? He said, listen, we've been in business for years. And we are reliable partners, and we have a lot of clients, and we have two choices. We cannot recommend to them something we know doesn't work. So we can either joint venture with you and recommend what works and keep our clients, or we're going to have to turn our clients over to you, and we don't want to do that. Okay, we're both in. To me, this piece document that we're looking at here is probably the single best credential that I can say or endorsement of F500 for lithium-ion battery. Why? Because Johnson Control is the largest foam manufacturer in the world. They're the largest dry powder fire extinguisher supplier in the world. They supply FM200, they supply Novak, and yet this is what they are pressing to their customers as the solution for lithium-ion battery. Here they mention why: stronger cooling, effective penetration, reduction of toxic exhaust gas, much safer. We first started out with JCI doing 9-liter fire extinguishers and a 50-liter. Now we have about 20 different fire extinguishers that are listed to the EN3 standard. Now I'll tell you, they're listed to an EN3A standard because there's no L standard to list to, which is my mission, is to push NFPA to an L classification for this, and then subsequent test protocols, because I think there's a lot of confusion in the world that, well, what's lithium-ion batteries, so what? It's not classified. It's probably an A. I'm really safe with my ABC fire extinguisher, and we just saw complete testing that invalidates that. Here they even put the Kiwa testing in here. They mentioned that the F500 encapsulator agent is good on solar storage, electrical cars, large battery areas. Here they talk about some of the features: high penetration of the extinguishing agent into the flammable materials, the encapsulation of liquid fuels, and the exhaust gases. So when you look at that video and the Kiwa testing, that gentleman who was doing the fire extinguisher testing, he did Monday, Tuesday, Wednesday, Thursday. On Saturday, they took him to the hospital because he had to get detoxed from HF poisoning, because he was not wearing SCBAs. He was wearing a fire coat. But as you know, a fire extinguisher is an incipient device. So, he was approaching it as though it's incipient fire, but he breathed in enough HF gas that he had to go and spend a week in the hospital detoxing. What subsequent tests have shown is that the F500 encapsulates the HF gas. So as a firefighter, if you're looking at, oh, I have one of these, you got the strong cooling, the permanent reduction of the heat, the encapsulation of the electrolyte, and now encapsulation of toxic off gas. And we've also quantified we're encapsulating the explosive off gas. And I'll show you a few more things. Fluorine-free agent. It's quickly and completely biodegradable. Has certifications for UL, maritime, navigation, a NATO stock number, pH is 7. So there's a lot of pluses here for the F500. And here you can see Johnson Control owns Tyco, York, Ruskin, Penn, Simplex. I think this test report, after we did the testing with Johnson Control on the fire extinguishers, we started to do more sprinkler testing. Johnson Controls has shared with us their presentation. This is their presentation about the fire extinguisher portfolios. I find this interesting, $30 billion annual revenue, 117,000 employees. Like I said, they're the largest in our industry, yet they're teaming up with the F500. And here we're showing the fire test. All these were done at a higher level, heat reductions. I don't want to run out of time, but this talks about the Environmental Hygiene Institute, biodegradable survey, water survey and assessment. Again, partnered up with Johnson Controls. One of the tests that we ran, and I think this is a significant test. Here we're taking an 1890, so this is very similar to what we did at Kiwa, and here we have a temperature range of the sensors was from 20 to 1400 C, and they actually topped out of 1400 C. So we're not exactly sure, was it above 1400 C or not, but in this experiment, they put the batteries into thermal runaway, had 8 temperature sensors in place. The agent is being delivered through 2 mist style nozzles at the 2% solution. Full data. Now this is what I find extremely interesting here is, so start the heating at 557, temperature increases, first smoke appears at 633, explosion of the battery pack at 657, at 702, power supply for the heat glow plugs goes off. At 734, we start flame formation at the battery package. At 802, we do the first shot of the F500 agent. So it's water and 2%, but do a 5-second burst. That's it, just 5 seconds. So from 802 to 807, we get an instant reduction of the flame and a big reduction of the heat. And then we're waiting. See, we don't do the second burst for another 30 seconds. So what we start to see here between 807, because this was a 5-second burst, and 825, so we got about 20 seconds, we get a little more flame, but much less flame formation. So decide, let's do a second 5-second burst. So now we do a second 5-second burst. So 10 seconds, we have no flame. Now we wait for 3 minutes. Still no flame. So from 8:33 to 11:27 is slightly under 3 minutes. So now we do a third 5-second burst. No flames are visible. And now we wait 3 minutes and we see that the temperature of the sensors have decreased continuously down to 80. There's no new flame formation. And now we're going to do another fourth 5-second burst. So we have gone here from 1400 degrees down to less than 80, less than 80 with only 3 5-second bursts of F500. And now we're waiting 15 minutes and the temperature is now continuing to decline down to 50 C. Here we can see that we've stopped the thermal runaway and the fire propagation to other places. So the glow plugs, the temperature increased to 1400. After introduction of the first pulse of F500, the temperature decreased to 400. Well, 400 is still above thermal runaway. But even though it's above thermal runaway, if you recall, we have a little bit more flame formation, but not much. It's because we're encapsulating the electrolyte, so we're resisting the electrolyte to be able to reignite. Then after the second extinguishment, a continuous decrease of temperature is obtained. So we got 10 seconds of agent, all experiments, no second fire formation was introduced, the extinguishment as described before. So they used 4.5 liters of the mixture to extinguish this fire and to prevent burn back resistance. This is showing the heat, the first 5 seconds, boom, the second 5 seconds. And again, after we stop the application of the F500, with plain water, we see that heat do this. It humpbacks and comes back up. With the F500, it keeps it down. They provide a summary here and say that it's due to surface tension reduction. I'm here to tell you it's not surface tension reduction. It's the spherical micelle that's causing this issue. The spherical micelle is changing the heat reduction properties of the water from steam conversion to thermal conveyance. Bosch did wetting agents, and Bosch experienced, just like water, the temperatures to come back up again. So a wetting agent doesn't have a spherical micelle. We saw the foam didn't work. They don't have the spherical micelle. So here we're encapsulating the electrolyte and we're changing the heat reduction, which is significantly reducing the heat and keeping it down. Now, here it's saying further experiments have performed on another lithium-ion battery package supports the interpretation of our results reported above. Thermal runaway was introduced to a battery and described, and we tried to delete the flame formation of battery using 50 liters of plain water as the extinguishing agent. However, the experiment failed. Even after a longer time of 20 minutes, there was continuously new flame formation. The second step was the same. So what they're saying here is the second time we used 5 liters, the first time 4.5. They had the same results 2 times in a row with the F500, but we couldn't extinguish it with the 50 liters of water. So I would like to say we're 10 to 1 more effective than water. The problem is the 50 liters of water did not extinguish the fire. So these 2 nozzles here go back to a 50-liter pressurized tank, and that's how they dispensed both the water and the agent. So on one hand, the 50 liters of water didn't put the fire out, didn't reduce the temperature, and on the other hand, 4.5 and 5 liters of encapsulator agent did. We have a remarkable technology here. This is another test, and I want to first show you, because one of the questions we get asked is, have you run your UL 9540 and 9540A test? And the answer is no. We've reviewed 9540 and 9540A. 2 weeks ago, we drove up to Indiana and reviewed it with Battery Innovation Center, and they all agree, and UL agrees, it's a testing of the thermal runaway properties of the battery energy storage system and not really a fire suppression test. So we are working with them to create a fire suppression test. The UL 9540 addresses really addresses the propagation, the thermal runaway, the radiant heat going to the second and third racks. And you can see this testing that we have done is done on the cell level, but it's also done on the module level. So we've installed several battery energy storage systems, but we don't just go and put a sprinkler nozzle into the container because we've never tested that. What we're doing is putting misting nozzles with a 3% solution of F500 inside the cabinet so that the solution of F500 can flow through into the rack and get on the fire. So we've created a system that does that. The secondary part of the system is the sprinkler head and inside the containers, and that's used mainly for encapsulation of HF gas and all the explosive off gases. So it's not that we're not going to run the test. We just have to make sure what testing we're running. I have about two more things here. So this is a battery from Jaguar in the UK. And you're seeing this off gas coming out of here, and then you're seeing the flame shooting out, because one of the questions gets asked us are how are you going to extinguish these if they're inside a compartment? Okay, remember we encapsulate fuel molecules, whether they're in a vapor phase or whether they're in a liquid phase. So what we have is electrolyte and hydrogen that are the electrolyte is being heated up and going to a vapor phase, and that's what we're seeing being ignited here along with hydrogen. So when we hit this, we encapsulate that fuel, cool that area, and take away the flame and our agent. It does reduce surface tension and goes into cracks and crevices to extinguish the fire and extinguish it quite quickly. So this is what I mean when we say we have testing at the cell level and also at the module level. Let me get to this is talking about the parts per million of the HF gas off gassing. This is one of the most recent tests. We've just got the test report. This was conducted maybe at the beginning of this year or November of 2021. And what they're simulating in this test is the battery that you would find in like a work truck like this. So here's the battery itself. It has different modules. So we can see 1, 2, 3, 4, 5 times 2, 10 modules. In this test, they're going to bring these up till they reach thermal runaway and they catch on fire. There is a thermocouple here in both of these modules, and there's thermocouples on the wall, and we're monitoring the temperature there. So in the UL 9540 test, one of the major things they're looking at is radiant heat. How is this heat going to propagate to the next stack and the next rack? That's what the same thing this is doing, is looking at that. I know we're running out of time, and I need to be careful. Okay, we're going to start the extinguishment here shortly. There's the discharge of the F500. 2 seconds. Flame was out. There it starts here. So what we're seeing is as soon as the agent hits that module, it's penetrating down into the module, and it's penetrating through any cracks and crevices based on the reduction of surface tension. And on its way in, those spherical micelles are A, rapidly reducing heat, and B, encapsulating any flammable gases and any type of electrolyte, taking that away. Now, this is the last video I'm going to show. Oh, no, I'm sorry. I'm going to show you one more because this was, both of these are through standard sprinkler systems that would meet VDS in Germany. Oops, sorry. Yeah, you can see up here thermally the temperature dropping very quickly. Just some of the potential clients: Formula One, Tesla, GM, TUV. This is the actual test report. And you see the testing was done back in April of last year. This is showing the test cells. This is showing the placement of the thermal couples. Here they show 2 ceiling-based sprinkler heads. Again, remember we have thermal couples on the module here, but there's 2 additional thermal couples here measuring the radiant heat. This goes on to talk about how the fire was started at 21. We get the heating element, took about 4 minutes. We see the first thermal runaway. These occurred on the left side of the battery. Extinguishment was started 1 minute later at 1:26. Based on the video, it's evident that, was only limited to the left side. You saw the rapid extinguishment. Here's the thermal couples, but I think this is quite interesting too, because here this was the heat of the battery right here, and then the left, this blue line was the right wall, and the red line was the left wall. So the battery was more towards one side, but you can see in all cases, not only are we hitting the thermal decline in temperature and the rapid decline that goes down on the battery, but also the radiant heat, boom, down on both sides. And then the radiant heat continues to fall. Even though we've extinguished and we shut everything off, your radiant heat still goes down. With water, what you end up with there, if you're doing plain water, is you're converting to steam. Now you have steam in there. It's actually driving the radiant heat up. So it's quite interesting technology. Here's a report. This came from China. This is research and development. I found this on the internet. I had no clue any of this was going on. We weren't involved in this, but here they talked about The efficiency of pure water, 5% F500. I don't know where they got 5%. Then they talk about 5% self-made solution. I have no idea what that is, but in this testing, they talk about extinguishment, the characteristics. They talk about the high temperature, large water consumption. Here they're referring back to the NFPA. Again, my position is pretty clear. Water is the biggest #1 Class A agent in the world, yet we need copious amounts to put this out. Perhaps this is not a Class A fire. And here it even talks about the complexities of these. So we're going to be pushing, and we hope that you in Australia will join us in trying to get these classified as a Class L fire. It talks about the NFPA, civil aviation, FAA. This is a problem throughout. Talks about Purple K not being effective. A study of fire extinguisher, the AFFF not working. Here they talk about F500 micro capsule technology. So yes, it's an encapsulator agent. They're not really referring to it the right way, but here they talk about they're using large volumes of water. They're referencing some of the DACRA tests. Here they're saying with the plain water, it took a long time to put out and it reignited, but with the F500, only 14 seconds, the water consumption was greatly reduced. A kind of microcellular agent, F500, can effectively inhibit Class D metals, which with no explosions. And it's also saying after they extinguished, it did not reignite. So again, this is a report that be glad to share with you. And then the last thing that I want to share, and then we open it up for questions, is this document. This is NFPA standard for water additives, fire control, and vapor mitigation. Note the year on here. This was just released in January of 2022. A lot of people say, well, if F500 encapsulator agent's so good, why aren't we using it? Why don't more people know about it? Well, I can tell you when I first started the company in 1997, we had about $500,000 in sales that year. And I can tell you probably today we had $500,000 in sales. So things are moving very, very quickly. The issue was back in 1997, there was no encapsulator technology standard. There was a foam standard and there was a wetting agent standard. We're not a foam. We don't create bubbles. Our technology is not based on bubbles. So by default, we had to be listed as a wetting agent. Well, wetting agents don't have spherical micelles. And we set forth to create a new standard that has encapsulator technology within that standard. And you're now looking at it, that was released in January of 2022. This is a significant technology. This is a significant advancement in the fire protection, fire industry. So I would say this is as significant as AFFF was back in the 60s. It's fluorine-free, biodegradable. Here, it talks about encapsulator technology, a spherical micelle stability test. So when you run, say, a UL 162 test, a lot of people think, well, that's a fire test. But if you take a step back and look at it's 180 degrees, it's really a bubble or film integrity test. If I have really crappy bubbles, I'm not going to put the fire out. I'm not going to control the fire in 1 minute, and I'm not going to extinguish it in 5 minutes. If I have average bubbles, I can control the fire in 1 minute. I can extinguish it within 5 minutes, but I'm not going to pass the burn back resistance test. So in order to control the fire in 1 minute, extinguish the fire in 5 minutes, and pass the burn back resistance test, I have to have quality stable bubbles that are stable in the presence of high heat. That's what this test is. This test measures, because what we're doing here is we're taking the test fuel, whether it's heptane, gasoline, diesel, and we shared this with Panasonic, and we said, you have a flammable electrolyte. Let's use your flammable electrolyte as the test fuel. So we take a test pan, we thoroughly wash it and clean it, we put the test fuel in, we add an amount of additive, and then we add water. And then within 1 minute, we put a torch to the surface of this, a 1500-degree torch. So what this is doing is we're putting in the water additive, the fuel in the water, we're mixing with kinetic energy. Our ratio that we use is 1 part of F500, 8 parts fuel, 40 parts water. So 1/40 is 2.5%. And the appendix talks about that. But there's a 1-minute ignition test after the agitation, but then you have to come back 2 hours later and put the torch to it. And it can't ignite after 2 hours. So at first blush, people think that, oh, this is a fuel neutralization test. No, we're using the fuel to demonstrate, does this agent create spherical micelles? Are those spherical micelles capable of encapsulating this fuel? And is that encapsulation stable in the presence of high heat over an extended period of time? Hence a 1 minute and 2 hour ignition test. When I show you the orientation of our molecules on the surface of the droplet, that is a big change in the fire protection world. So now you would never dream of putting plain water onto a Class D fire, because it would break the H2O molecules into hydrogen and oxygen, and both of those are flammable explosive gases, and you have lots of fireworks. Well, if you recall, we have changed the substance on the surface. We have an F500 molecule on the surface. So now, because of the advent of this technology, there's now a need to conduct a Class D test. So this standard in the latest revision added Chapter 9, which is a Class D fire test. The only Class D fire test that existed prior to this was UL 711, which was for fire extinguishers only. So now we have a whole market change. We're recycling batteries, we're recycling metals, and you have a very large Class D metal fire. What is the fire department going to do? Bring 10,000 fire extinguishers to the site to put it out? No, this technology is now allows us to move forward and get a listing, and gives you a mechanism to fight big Class D and lithium-ion battery fires. Now, the last thing I want to show you is in this standard, it talks about lithium-ion battery. Lithium-ion battery and lithium-ion battery energy storage systems, BESS fires, are unique electrochemical fires that involve Class A, B, C, and D within one entity. While battery energy storage systems are covered by NFPA 855, it should be noted lithium-ion batteries as a standalone hazard are not currently addressed in any NFPA standard. Okay, so we're dealing with lithium-ion batteries in laptops, iPhones, Tesla cars, GMs, Volts, e-cars, hybrid cars, all kinds of extraction equipment. Now they're coming out with e-buses, e-scooters, e-things. But this fire suppression, this hazard's not addressed in any standard until today. So according to the research reports, copious amounts of plain water are required to extinguish lithium-ion battery fires. And they can still have thermal runaway up to 72 hours later. Now, water additives based on spherical micelle technologies encapsulator agent conforming to section 7.7 have been extensively tested by independent third-party testing. Kiwa, I showed you that. Dacra, I showed you that. Daimler, I showed you that. Bosch, I did not show you that. Fraunhofer University and TU Clausthal, you saw that. This testing has been controlled, scientific, highly instrumented, documenting fire suppression, control, elimination of thermal runaway, and encapsulation of both flammable electrolyte and other explosive off gases, rendering them non-explosive. Encapsulator technology reduces toxic HF gas exposure. Okay, so the technical committee has reviewed all of this, and now we have a worldwide standards organization putting authenticity to the documentation that I'm talking to you about today. If this is a little disjointed, I apologize. I didn't want to come do a PowerPoint presentation. I wanted to share 14 years of scientific testing so that we don't recreate the wheel here, that we can move forward. Here is a standard that recognizes encapsulator technology for lithium-ion battery. In addition to copious amounts of water used to suppress lithium-ion battery creates copious amounts of runoff containing hydrofluoric acid, creating environmental issue and an expensive hazmat disposal cost. Compared to water, water additive solutions use a reasonable amount of solution has been documented to modify the chemistry of the water runoff, making it suitable for additional dilution and disposal to a municipal wastewater treatment plant. Testing documentation can be found here. So we're in the process of working to get this documentation uploaded to the NFPA research library. Excuse me. And I can tell you that was quite a last couple of days of discussions with a lot of different people and a lot of different technical committees and people over what we're discussing here. With that it, I would say thank you, and I'm going to open it to some discussion or questions.